Okay, we're going to talk about the reaction quotient. It is the same thing as the equilibrium expression, but you use values for concentrations that are not at equilibrium. So to calculate the Q, the value of Q, you just put in the concentrations for the system into the same expression for the equilibrium constant. What this allows us to do is to compare where the system currently is to what the system needs to do to get to equilibrium. So if you calculate a value for Q and it's equal to K, the same value, the system's already at equilibrium and there will be no shift in the system. If Q is greater than K, okay, and remember that K is equal to the concentration of the products at equilibrium over the reactants at equilibrium. So Q then is equal to the products at whatever situation over the reactants. If Q is larger than K, then there's too much product. This number is too big, so the equilibrium is going to shift to the reactant side or to the left to decrease Q until the value of Q is equal to K. Similarly, if Q is less than K, then there's too much reactant and the equilibrium is going to shift to the product side until the value of Q is equal to the value of K and the system attains equilibrium. Okay. So we can use this Q to predict the direction that the system or the reaction will shift to get back to equilibrium. So we have this hydrogen and iodine making hydrogen iotic. I said that really weird. Anyway, K is equal to 50.5. Okay, we're given a temperature 448. We're given the moles of the two reactants, the moles of the product. I didn't highlight that in the right order, and we're given that the container is 2 liters. So we want to predict the direction in which the reaction is going to shift. So we're going to be looking for Q. The expression for Q is the hydroiotic squared over the concentration of the hydrogen and the concentration of the iodine. Now, they give us moles and a 2-liter container, so the first thing that you're going to have to do is calculate what is the concentration of the hydroiotic. Well, that is the 2.0 times 10 to the negative 2 moles over 2 liters. And that would be 0.01 molarity. Similarly, your concentration of your hydrogen and your concentration of your iodine will be, so your concentration of your hydrogen will be 0.005, concentration of the iodine 0.015. So looking for the value of Q, I would get 0.01 squared over 0.005 times 0.015. So Q is then equal to 1.3. Hopefully you can see that is much less than the 50.5. So I need to increase the product concentration. The equilibrium then, or the system, will shift to the product side, shift to the right, until it reaches equilibrium. We'll be looking at this one in class. If you would like to do that and come in with the answer, that's fine. Okay. So now we're going to talk about the Chateliers Principle, and this really kind of builds off that concept of Q relating to K and being able to tell which way the equilibrium will shift to maintain or get back to equilibrium. Specifically, the Chateliers Principle states if a system at equilibrium is disturbed by a change in temperature, pressure for gas systems, or the concentration of one of the components, the system will shift its equilibrium so as to counteract the effect of the disturbance. Okay, so any change in that equilibrium, any change in the equilibrium conditions upsets the equilibrium system. A system under that stress is going to shift to relieve the stress and get back to equilibrium. There will be a change in the rate of the forward or reverse reaction until the system gets back to equilibrium, and then those two rates again will be equal. Okay, let's look at the effect of adding a reactant to an equilibrium system. So we're going to consider the reaction of hydrogen reacting with fluorine to produce HF. Okay, if I add more H2 or F2, if I add more of a reactant, there's going to be an increase in those number of collisions. That is going to affect my rate of the forward reaction. Okay, it's going to increase and it's going to form more HF product. And it's going to continue to do so until the equilibrium or new set of concentrations are reached, until Kc, the value of Kc is again reached. So the effect of adding reactants shifts the equilibrium to the product side. So what is the effect of adding product to the equilibrium? Okay. Say I add more HF. So there's an increase in the number of collisions of my HF molecules. That means I'm going to increase this reverse reaction, okay, because I have increased concentration, and I'm going to then increase the concentration of those two reactants until the value of K is then reached. So the effect of adding more product is to shift the system to the reactant side, to the left, until equilibrium is again reached. Okay, so if you add reactants, the equilibrium is going to shift to the product side until equilibrium is then reached. If you add more product, it's going to shift to the reactant side until equilibrium concentration is again equal to K. Sorry. What happens if I remove reactant? Okay, so say I decrease, oops, I gave it away. Okay. If you remove a reactant, you're going to decrease the number of collisions, right? So you're going to decrease the rate of the forward reaction. It's going to shift the equilibrium back towards the reactant side until equilibrium, a new set of concentration is reached equal again to K. So the effect of removing a reactant is to shift the equilibrium to the reactant side. What if I remove product? Okay. Again, if I remove product, it's going to increase this, it's going to decrease the backwards rate, okay, increasing the amount of product made, and it's going to establish new equilibrium concentrations, again being equal to K. So let's look at summary of the changes. This table is pretty good. Hopefully you can logically figure out which way the equilibrium is going to shift as opposed to memorizing a table. Okay. So let's look at these predicting any shift in the equilibrium for each of the changes in this reaction. Pause. Okay, come up with the answers for A, B, C, and D, and then I'll come back with the answers written on the slide. Okay, here are the answers that you should have gotten. H2S being added, okay, since this is a product, it is going to shift the equilibrium to the reactant side. This one might have been a little tricky, all right? NH4HS is a solid, so adding more of it is actually going to have no change, because remember, in a heterogeneous equilibrium, a pure substance does not appear in the equilibrium expression. Okay. If NH3 is removed, NH3 is a product, it's going to shift it to the product side, and the same with the H2S. I'm going to pause this. How about the effect of decreasing the volume? Okay, so when a reaction at equilibrium contains different number of moles of reactants than products, and this is in the gas phase. Okay. A decrease in volume. By decreasing the volume, remember, you're changing this, the volume part of the molarity expression. So it effectively increases the concentration of all of your components. Okay, and it upsets the equilibrium. The effect is that the equilibrium for a gaseous system, when I decrease the volume, it is going to shift the equilibrium towards the fewer number of moles. So if you look here, I have 4 moles of gas on the reactant side, I have 2 moles of gas on the product side. If I decrease the volume, it is going to shift the equilibrium towards the side with less moles. I'm going to skip over those. If I increase the volume, okay, it's going to move towards the greater, oops, sorry, whoa. It's going to shift the equilibrium to the side with the more moles. And again, this is for a gas system. Okay. Interestingly enough, and this is kind of important to remember, if I change the pressure by using an inert gas, I do not change the concentration of any of the gases currently in that system. So there is no shift in the equilibrium if I change the pressure of the system by adding an inert gas. Changing the volume will shift the equilibrium, okay, depending on whether I increase or decrease. If the volume is increased, the pressure is decreased, the equilibrium shifts towards the more moles of gas. But adding an inert gas does nothing to shift the equilibrium. Let's look at the difference or the effect of temperature on the shift in equilibrium. And we're going to have to look at exothermic and endothermic differently. So for an exothermic reaction at equilibrium, remember that we can look at that heat as being a product. If I increase the heat, it is pretty much, or it is the same effect as increasing the concentration of a product. Increasing the concentration of a product is going to shift the equilibrium to the reactant side. If I decrease my heat, okay, I'm decreasing the concentration of a product, it is going to shift the equilibrium to the product side. And it all pertains to looking at where that heat goes. Talking about an exothermic reaction, the heat is considered a product. So if I look at an endothermic reaction. Okay, I put my energy on the reactant side. If I decrease the temperature, okay, I'm decreasing the concentration of a reactant. My equilibrium shifts to the reactant side. Conversely, I lost all my writing, sorry. I think I hit the wrong thing. I did hit the wrong thing, sorry. Having trouble. Okay, so again, endothermic heat as a reactant. If I increase temperature, it is going to shift to the product side because I'm increasing the concentration of a reactant. Okay. The only thing to note, okay, and hopefully, okay, temperature changes are actually going to change the value of your K, because remember, K, your equilibrium constant, is really related to your rate constant. Rate constant changes with a change in temperature. Your equilibrium constant changes also with a change in temperature. Okay. The other changes just, here's a nice summary. Little thing to note here is the effect of a catalyst. Remember, catalyst works because it lowers the activation energy by changing the pathway. So all it does is it increases both of the forward and the reverse rate equally, and there is no effect on the equilibrium when I add a catalyst. Okay. Take a moment to look at those, pause, and then we will show you the answers in just a minute. And here are the answers you should have gotten. Please come in with any questions, and that should be the end of this screencast.